In this video, we present our paper I Am Portrait, Learning 3D-aware Video Diffusion for Photorealistic Talking Heads from Monocular Videos. Given target expressions and a reference portrait, our goal is to transfer expressions and head poses from the target to the reference, while ensuring the generated results are 3D-aware. However, existing methods struggle to meet this goal. Approaches based on warping 3D implicit feature volumes suffer from multi-view inconsistency. Others that warp feed-forward 3D representations often produce stiff expressions. Methods based on 2D video diffusion generate natural expressions and high-quality videos but lack 3D awareness or require extra diffusion processes to support novel view synthesis. Therefore, our goal is to generate photorealistic and natural motions in a 3D-aware manner. Moreover, our training is based on monocular videos in the wild. Our framework builds on the concept of diffusion with forward models. It takes a reference portrait and target expressions as input and generates MPI sequences that support novel view rendering without requiring additional diffusion steps. Specifically, we use a video diffusion model as the backbone, split into a color branch and a geometry branch. The model is conditioned on the reference portrait and its corresponding 3D UV map. Inputs include noisy images and target expressions, and the model outputs MPI sequences whose frontal views match the target expressions. For long video generation, the rendered frontal view of the previous MPI sequence is used as the first frame condition. We then analyze the challenges in this task. Ideally, training would require multi-view data as supervision. The diffusion model could take noisy videos from one view as input and be supervised using the other view. However, such datasets are not readily available. To address this, we propose a novel training framework. During data preparation, we use 3D fitting to extract target expressions and target cameras from the video. UV maps of the target video are obtained by rasterizing the meshes of target expressions to the target cameras. Then, we randomly select a reference image from the target video and find the corresponding reference camera from the target cameras. By rasterizing meshes of target expressions to the reference camera, we get UV maps for the pseudo-GT video. This pseudo-GT video is then generated using these UV maps. The core idea of our training framework is to generate and use pseudo-GT videos as denoising inputs. By adding noise to imperfect pseudo-GT videos, using them as inputs, and supervising the model outputs using real collected videos, we approximate the benefits of a multi-view dataset. To be specific, our reference target alternating training framework includes two branches. The top branch constructs MPIs in the target camera and renders the frontal view, where we directly use the real-world target video to supervise the model. This branch bootstraps the model and helps the model learn sharp renderings. On the bottom branch, we construct MPIs in the reference camera and use the bootstrapped model to generate pseudo-ground truth by rendering the frontal view. The pseudo-ground truth is added with noise, serving as the model input, while the real-world target video is used to compute side view loss for learning 3D shapes. Please refer to our paper for more details. Next, we show comparisons with existing methods. Face V2V gives stable results and follows the input identity, but produces fewer details due to its low output resolution. Emo Portrait gives sharper results, but suffers from larger identity shifts. Portrait 4D V2 produces good sharpness and fewer identity shifts, however relatively stiff expressions. The diffusion-based methods follow your emoji and X-Portrait render good high-frequency details, but do not precisely follow the input head poses or expressions. In contrast, our method, which is built upon a native video diffusion model, gives good video and image quality, faithful identity preserving, while following the input control signal. We further show novel view renderings. Since we use MPI as our scene representation, the generated talking head videos do not support rendering from excessive camera viewpoint changes. However, our method can still generate reasonable stereo videos for viewing purposes. Here, we show long video generation results. We use the reference portrait shown in this slide as a condition and two target expression sequences as controlling signals. Each generated video is more than 30 minutes long. We use the first frame condition to concatenate two adjacent clips. Using a scheduled classifier-free guidance strategy, our method maintains stability and smooth motion over extended durations. Here, we show generated results when taking synthetic images as reference images. Despite being trained on real-world data, our model generalizes well to synthetic inputs, even with large color distribution differences. Finally, we demonstrate stereo renderings for VR headset viewing. Please visit our project page for more results. Thanks for watching.